In the last module, we introduced the constant wall temperature case for the analysis. We had completed the constant wall heat flux case. So, in the constant wall temperature case, I think we had left with the definition of arithmetic mean temperature as the driving temperature difference. Let us just quickly get to that. So, constant wall temperature case is accomplished by either having a condensation or phase change boiling process, condensation or evaporation to ensure T wall equal to constant. So, because at constant pressure evaporation or condensation is a constant temperature process. So, you would in a typical environment, if you want to heat this fluid at constant wall temperature, T wall equal to constant, then you would ensure that there is evaporation or condensation. So, if you want to put heat into this fluid, then the fluid has to give away heat. So, this should be either condensation or evaporation on this side to ensure T wall equal to constant. So, if I plot the temperature distribution, this could be the temperature variation of the fluid which is getting heated. This is T wall equal to constant, and this is T cold I, T cold exit, or TMI, TME, and as can be seen, the driving temperature difference delta T as a function of x is T wall minus T bulk mean local. So, wall temperature minus local bulk mean temperature of the fluid. So, local fluid temperature. So, this potentially varies along the flow direction. As you can see, this delta T, if I plot as a function of x, it is going to continually decrease along the flow direction, and we know that Q is directly proportional to delta T. So, the heat transfer in every subsequent region. So, if I increase the length from say xn to xn plus 1, the additional heat transfer that you get in that additional length is going to be smaller than what you would have got in the previous delta x region. Okay. So, Q between delta x and delta x minus 1 would be greater than Q between delta x and delta x plus 1. Okay. So, each additional incremental length causes a reduction from the previous incremental length in terms of the heat transfer. So, many times having length which is going on tending towards infinity or extremely long length of the device or heat exchanger is not going to be very profitable from point of view of improving the performance greatly. We will see that in a few minutes. So, we said that inlet temperature difference delta T I is equal to T wall minus T bulk mean inlet, delta T exit is T wall minus T bulk mean exit. We will keep these definitions for use later on. And if we have the same assumptions as steady state. So, the same assumptions for energy balance, steady state, constant m dot, properties constant, diameter constant, fixed diameter, then all heat from the fluid goes into change in temperature or sensible heating only. Negligible changes in potential and kinetic energy. So, these no volumetric heat generation. Okay. So, if we list these assumptions and proceed for the basic energy balance as we had done before, we can write for a control volume given as shown here. This is a pipe of diameter d. This control volume is of thickness dx, m dot Cp T bulk mean, and this is your local heat flux Q double prime of x. Remember, q double prime of x is not equal to constant. Why? Because T wall is equal to constant and we cannot keep both heat flux and wall temperature as constant in a given problem. So, if I write the energy balance, we start with our favorite equation E dot in minus E dot out plus E dot generated equal to E dot stored. At steady state, assumption 1, this goes off, no volumetric heat generation, which is your assumption number 5 there. So, E dot in minus E dot out is equal to 0. I can write m dot CPT bulk mean at any location plus q double prime local pi d dx is equal to m dot Cp Tm plus dTm. What is coming out is Tm plus dTm, same mass flow rate, m dot same thermophysical property Cp. So, if I segregate the variables, I get m dot Cp dTm is equal to q double prime local pi d dx, or if I make this a little tractable, I get dTm by dx is equal to q double prime local, I continue to use this bracket as a function of x, divided by m dot Cp. This is exactly what we had derived earlier for heat flux equal to constant case, because nowhere in the derivation, nowhere in doing the energy balance have we invoked the constant wall temperature assumption. We just started with the basic energy balance. So, the equation lends itself to an identical form, except that q double prime of x is a variable now. And instead of, if I have to integrate this, I would have integrated in the earlier case, and this q double prime x would be a constant, pi d m dot Cp, everything was a constant, we would get a linear temperature profile, and that was quite straightforward. Because q double prime x is a variable, we have to write it as q double prime into pi d dx heat transfer rate is equal to local heat transfer coefficient times T wall minus T local into DAS, surface area, elemental surface area. What is the elemental surface area? Pi d dx. Okay. So, this now is going to be replaced there as, so I can write dTm is equal to q double prime of x pi d dx divided by m dot Cp is now the same as h into pi d Tw minus T local dx divided by m dot Cp. I am merely substituting for the q double prime pi d from above. Now, I need to segregate the variables dTm by T wall minus Tm local. Please remember, this is local temperature difference. I will drop off the bracket x just to maintain simplicity in writing. This is going to be equal to, you get h into pi d divided by m dot Cp into dx. You can also transform this as d of d Tw minus Tm, Tw minus Tm, okay, this one. dTm is nothing but derivative of T wall minus Tm. What is the derivative of T wall minus Tm? T wall is a constant, remember, dTw minus Tm is equal to dTw minus dTm. What is derivative of T wall? 0, because it is a constant. So, we have written the numerator of the left hand side just by a simple manipulation this way. There needs to be a minus sign which we are going to absorb in the right hand side, pi d dx by m dot Cp. Now, you have a function which is d of a quantity divided by that quantity, which on integration is going to give me, integrate with respect to x and within limits from x is equal to 0, where T bulk mean is equal to T bulk mean inlet, x is equal to L, T bulk mean is equal to T bulk mean exit. So, if I do the integration, I would get d of T wall minus T divided by T wall minus T bulk mean integrated from delta T inlet to delta T exit, correct. You are going to have the variable is T w minus T m. So, at x is equal to 0, the difference in the temperature is T w minus T m I. Remember we had this here, the first slide we had shown this. So, the inlet temperature difference, exit temperature difference, this is what is used as a limit. When I use that as the limit, the right hand side just remains minus h pi d by m dot C p dx integrated from 0 to L. Okay. So, this is log of T wall minus T main exit divided by T wall minus T bulk mean at inlet on application of the limits is equal to minus h pi d L by m dot C p, which on separating you would get delta T bulk mean at exit divided by delta T at inlet is equal to exponential minus h into pi d L is nothing but the surface area m dot C p. Pi d L is nothing but the surface area. So, if this is a pipe, this is 0, this is L, this is my diameter d, surface area is pi d L. So, the delta T exit, that is T wall minus T bulk mean at exit, I can now write this for any local location, T wall minus T bulk mean at inlet is equal to exponential minus, instead of integrating from 0 to L, I would integrate from 0 to any local x. H into pi d is same as a perimeter. So, I can just write it as perimeter times dx divided by m dot C p. This is a general form of the same equation. What does this tell me? It tells me that the driving temperature difference, this is numerator, I can call it local delta T divided by initial delta T, driving temperature difference is exponential to constant times x, where constant C1, let me call it C1 is equal to Hp by m dot Cp. So, locally you can say H is a constant. So, you can call this Hp by m dot Cp, and this tells me that there is an exponential decay in the local delta T, which means there is an exponential decay in the heat transfer which is taking place along the length, and that is what we had shown in the first slide. This is your delta T local, this is your delta T initial, there is an exponential decay. This is an exponential curve, the difference is decreasing exponentially. So, this is going to help us understand that if I were to calculate the bulk mean temperature at any particular location, I need to know the right hand side and I need to know the maximum or the initial temperature difference, and the local bulk mean temperature can be calculated. The same analogy can be extended to, instead of H, what is H into A? H is nothing but the heat transfer coefficient and P dx is nothing but the surface area. What we can do is, this is when the outside is at T wall, okay, and this is the T bulk mean local, correct. So, my heat transfer is only convection between the heated surface and the fluid. So, if I were to write it as a resistance, this is the driving temperature difference delta T divided by the convective resistance. that is my heat transfer, everybody agrees. So, Q double prime is nothing but local T wall minus T bulk mean local. This is my driving temperature difference divided by the convective resistance. Instead of having a single resistance, I can extend this to a case where I have multiple resistances, and the multiple resistances comes from the fact that you are going to have this as the T wall, this is the bulk fluid which is flowing, T bulk local, and instead of this being held constant, you could have a layer of this could be the pipe material, there could be a finite thickness associated with it, there could be some kind of a sandwich material, another material, or you could have an insulation. So, whatever be the problem, I can have multiple barriers for heat transfer, and these multiple barriers would serve as additional resistances for heat transfer here, and I might have condensation or boiling happening on this side. T is equal to constant, I can have T infinity is equal to constant on this side, wherever this is, mind you, this is a circle. So, I can have T infinity is a constant on the outside, and I have two additional insulating resistances here. This is one, this is the other, and this is your central pipe. Okay. So, if I were to do that, I will say here the resistance network would be T infinity, there is convection to this solid surface, then there is conduction here, another conduction, and then another convection. This is T mean local. So, I will write it, I will draw the resistances this way, it is easier. 1, 2, 3, 4. This is outside convection, this is inside convection, this is black, let me write it with black color, this is insulation resistance, this is, I have written it in green. So, this is like wall resistance, and this is T infinity constant, this is T bulk mean local. So, let us call this T S 1, T S 2, T wall, or T W 1, T W 2, T W 3. So, T W 1, T W 2, T W 3. What are the resistances like? Resistances outside convection would be 1 by H naught A naught, this is 1 by H I A I. A naught is pi D naught L, this will be pi D I L, this is my D I and this is my D naught, and this is say D 1 and this is say D 2. So, this is going to be insulation is between D naught and D 1. So, this is log of D naught by D 1 divided by 2 pi k insulation L. This is log of D 1 by D 2 divided by 2 pi k wall into L. So, these 4 resistances would act in series, and your driving delta T, T infinity minus T bulk mean of x divided by sum of R total or thermal resistance is going to be your Q double prime, right. This we have seen in conduction, these resistances were there, and in convection we have got means to calculate this H naught and H I. So, this is constant, this is like your wall temperature what we saw, this is your local bulk mean temperature, and this is going to vary exponentially as I progress in the flow direction. So, if I were to plot this again, T as a function of x, T infinity is constant, T bulk mean is varying with respect to x, and hopefully this TW1, TW2 etc. would be something like this. These would be the intermediate temperatures. So, TW3, TW2, TW1. I do not know what the nature would be, but there would be something in between these two. So, this is T bulk mean inlet, this is T bulk mean exit, this one. Okay. So, what I am trying to say here is the same concept that was derived for one resistance associated with heat transfer, namely 1 over this one H into A, can be replaced by a sum of resistances. The sum of resistances is nothing but R1, R convection outside, R conduction insulation, R wall, R convection inside. This is 4 resistances, 1, 2, 3, 4. These summation of R is nothing but R convection outside plus R insulation plus R wall plus R convection inside. These 4 can be calculated knowing the dimensions and the outside and inside heat transfer coefficients, and the total resistance can be calculated. Once this is known, this can be extended as Q double prime is equal to delta T divided by sum of R total, and this is resulting in an equation which looks like this, where U times A is nothing but 1 over summation of R total, and this U is called as the overall heat transfer coefficient. This is something you need to emphasize to your students. U takes the same role as H. Okay. So, if you just compare this, U times A is 1 over the summation of resistances. Instead of one resistance, there is sum of resistances, and the role of U is like H, except that instead of one value, it is the summation of values of the resistances. And keep in mind, for a given situation, R total is constant, therefore, U times A is constant. So, very important observation, very important deduction. U times A is always a constant because it is nothing but the reciprocal of the total resistances. Given geometry, given thermal properties, thermophysical properties, the resistances would be constant. Given flow rate, suppose mass flow rate on the outside and the inside are fixed, which is what is the case in most applications, then H I and H naught once calculated would remain the same. The thermophysical properties, that is the thermal conductivity of the wall, insulating materials do not change with temperature, they are virtually constant. So, the resistances are also fixed, therefore, all the resistances that we have will be fixed. What does this mean? The product of U into A. Why? Because this R total, if you look, has been defined with H naught A naught, H I A I. This is basically taking care of the varying radii because of this log term. So, everywhere the area term is embedded. So, I can have, instead of U A, what area do I take? I can say 1 by R total can be expressed in terms of outside area, inside area, or any intermediate area based. How many intermediate walls do I have? I have two additional surfaces, that is diameter D1 and D2. So, I can have U based on D2 A D2 is equal to U based on D1 A D1, U naught based on outside area, Ui based on inside area. Whatever be it, the product of U and A, the same subscript, you should note that. the same subscript needs to be there, that is all equal to 1 over R total, summation of 1 over R total. What does this lead us to? This means that U naught is not equal to constant. The product of U times A is constant. The product is constant, but not U. Okay. So, from this what we can say? We can say that this quantity which we have defined, which is h times P dx. So, this delta T, which is local divided by delta T inlet, is nothing but h into As, can be replaced as U times A divided by m dot Cp, where h times As is being replaced by U times surface area. Okay. This is just an analogy between one resistance and multiple resistance. This quantity HAS by m dot Cp has a very important name, which is called as number of transfer units. Number of transfer units. It represents basically area and the effect of the heat exchange that is going to happen because of each additional incremental length that is added. So, NTU or dimensionless parameter NTU is basically a measure of effectiveness of the heat exchanger, effectiveness of heat transfer. Okay. So, let us take a simple example. If I have a flow of inlet fluid coming at 20 degrees centigrade, surface is at 100 degrees centigrade, I want to calculate the exit temperature. So, if I put NTU is equal to HAS by m dot Cp and T exit I calculate, NTU of 0.01 gives me T exit of 20.8, 0.05 gives me 23.9, 0.5 gives me 51.5 as exit temperature, 1 NTU gives me 70.6, 5 gives me 99.5, and making it 10 gives me 100. The point to note here is, as my NTU increases, the effectiveness of heat transfer increases, and therefore, the exit temperature progressively increases. But if you notice these two, if my area has gone twice, HAS m dot Cp, everything remaining constant, only length is changing, this is increased by a factor of 2. It causes a change in the exit temperature by 0.5 degrees. What it means is that every additional incremental delta x or increase in area or length causes smaller and smaller increase in the outlet temperature, or the effectiveness or usefulness of the heat exchange drops as the size goes on increasing in this case. And therefore, if instead of increasing this to NTU of 10, so NTU of 5 versus NTU of 10, size is twice here, and the material cost etc. is going to be double. So, increasing by a factor of 2 causes only a 0.5 degree change in the exit temperature. I would rather stick with NTU of 5 and be happy with 99.5 as exit temperature than go and increase it to 10 for a 0.5 degrees, right, a 0.5 degree change in the exit temperature. This is very useful in determining the size of the heat exchanger and makes us decide how long tube that we need to employ, what is practical, what is cost effective. Okay. So, based on this constant wall temperature derivation, we have come to a very useful non-dimensional quantity which you will use in heat exchangers, which is called as NTU or number of transfer units, which represents the size of the heat exchanger or the effectiveness of the heat exchanger for a given set dimensions. Thank you.